In this video, we're going to take a look at some hard start kits. Specifically, we want to talk about the hard start kits that are used on air conditioning systems, and most often you're going to find these on residential and light commercial. You will not find hard start kits on three-phase air conditioning systems. So again, we're talking residential, light commercial. They're pretty often used, especially with some of the newer refrigerants and some of the larger systems and more efficient systems. How often they are very frequently misunderstood on both the installation and the troubleshooting. The purpose of a hard start kit is that it provides additional starting torque to a compressor to overcome refrigerant pressure differentials. Basically, if we have pressure on one side of the compressor, no pressure on the other side, okay, we have to overcome a pressure differential to get that motor to start turning. It also provides additional starting torque when the starting amperage can have an effect on the rest of the building. Okay, if you have a customer where the lights are dimming when the compressor's starting and everything checks out okay in the system, you may need to consider putting a hard start kit in. I also know that we use them on a lot of buildings with solar. Okay, if we have a solar system on a house and we want to avoid the heavy load when a compressor's starting, we can put a hard start kit in and it will assist with that. A hard start kit is a prepackaged combination of a start relay and a start capacitor. Most air conditioning hard start kits are using potential relays as the start relay. And I'll go into that in a minute, but if the relay has this side up written or stamped on it, it is most likely not a potential relay, and these instructions are not going to apply. So again, take a look at that start relay that's a part of the kit. If it has this side up written or stamped on it, you need another set of instructions, and this video will probably not apply. Size matters. Make sure the kit you select matches the size of the compressor. Some kits are rated by horsepower, some kits are rated by the tons of cooling. Use a kit too big, you'll burn out a compressor. Use a kit too small, it won't provide the starting torque that's needed. So again, try to make sure you look at the packaging. It will tell you the size of system that the hard start kit will work on. Before installing a hard start kit, check the compressor. Okay, there's no sense in putting a hard start kit on a compressor that has damaged motor windings. So take a minute and check all windings to ground. Also check a winding to winding. Take a moment to check the existing run capacitors. Again, don't sell a customer a hard start kit when you also have a bad capacitor. Take a moment to check what's there first. The parts of a hard start kit: you have a potential relay, which has pins 1, 2, and 5, and I'll go into the wiring in a minute. And you have a start capacitor. Start capacitors are normally plastic housing, and they have microfarad ratings of over 60 microfarads. So again, plastic housing, they do have a resistor on them most often as well, a bleed resistor, and it will have over 60 microfarads. This is just an example of a hard start kit, okay? I just pulled it out of a catalog picture. Okay, you have two terminals on the top of the capacitor. You have a little bleed resistor there. It's plastic case. Okay, and then you have 3 terminals on the potential relay. So the wiring diagram for a hard start kit, basically it takes our PSC motor, which is just the run, com, and start with a run capacitor, and we add a start capacitor and the components to take it out of the system when the compressor's running. Because start capacitors we do not leave in the circuit once the motor's turning. Okay, we have pins 1, 2, and 5. Okay, we have a run capacitor that's existing, and we have our start capacitor that we wire in. Don't be a hack when you're putting this stuff in. Okay, this is not how to add a start capacitor, hard start kit to a system. Okay, we don't want to see just loose components laying around a wiring compartment. We don't want to see cardboard boxes in there. This is all a fire hazard. This is also an electrocution hazard. Think about if one of those terminals touched that housing and our ground wasn't good, What would happen to the kid or the pet that came along and touched the case of the unit? So again, this is just not a good idea, and you'd be surprised how often we see this. Use a metal strap and screws to hold all the components in place. Don't leave loose in the wiring compartment. Remove the cardboard boxes. These are a fire hazard. Zip tie excessive wire lengths and use crimp connections to wire to the terminals. And again, as always, be safe and turn off the power at the disconnect or the breaker before you do any of this. Follow the wiring diagrams provided on the packaging. Normally, from the common on the run capacitor, it will be a C terminal. One wire goes to the new start capacitor. From the second terminal on the start capacitor goes to pin 1 on the potential relay. From pin 2 on the potential relay, we go to the start winding on the run capacitor. That's going to be the HERM terminal. From pin 5 of the potential relay, you want to go to the same point in the circuit that the compressor common terminal is wired to. You have to look at this, okay? Many systems do this differently, but most often you're going to find this on L2 of the contactor. So again, from pin 5 of the potential relay, go to the same point that the compressor common terminal is wired to. Again, always look. Don't just trust the wiring diagram that's on the inside of the door because people have moved stuff around eventually. So this is just 2 examples, okay? The one on the left just has a standard 2-pole run capacitor, okay? You're going to, again, you're going to take from the T, which is basically the equivalent of the common, okay? That's the power feeding the run capacitor. We're going to go to our start capacitor in pin 1, out of 2 to the same point of the capacitor, the start windings on, and then pin 5 goes to the common. On a 3-pole dual run capacitor, you notice we have the fan terminal as well. Again, the C terminal to the start capacitor, and then to pin 1. Pin 2 goes to the HERM terminal, which is the same point the start windings wire to. And pin 5 goes to the identical point the common on the contactor's wired to. Now be very careful because we have 2 commons here, okay? Common on the on the run capacitor is not the same as the compressor common. A lot of times people make the mistake of putting pin 5 back here and it will not work properly. Okay. So just, again, it's very easy. The start capacitor gets wired to basically the same point the run winding does. Okay, in other words, constant power feed once the contactor comes in. Pin 2 goes to the start winding, the HERM terminal, and pin 5 goes to wherever the common terminal of the compressor is wired to. Test everything before you leave. Don't just leave, okay? How are you going to test this? You're going to start the system up and you're going to take amperage readings, okay? You can also take a reading very, very carefully across pins 1 and 2. When the system is up and operational, you'll get a voltage reading between 1 and 2 if everything's working properly. If it's not working properly, you will not get a voltage reading between 1 and 2 because the switch will remain closed. Neatness counts. Okay, you want systems to look neat when you're done. Okay, you want everything to be mounted in place. For example, the start relay, the white box over here, is screwed up to the housing. The start capacitor has a metal band on the housing. You can buy these metal bands in rolls. Okay, use a sheet metal screw. Don't go into the coil if you are close to the coil behind it. Now, troubleshooting, you have 2 components you're going to have to troubleshoot with a hard start kit. You have the relay and the capacitor. Each one of them has to be troubleshooted. So make sure the power is off and discharge all capacitors before you even start this. Look for obvious damage to the capacitor. Look at the top sides. Look for the little safety relief hole there. Look for damage to the resistor. You're looking for burn marks or anything that has signs of like a voltage surge or water or rust. Look for damage to the terminal connectors. Okay. Test with a reliable capacitor checker. Make sure you're within the tolerance. Capacitors are not that expensive. Replace it if anything is not correct. A capacitor is a lot cheaper to replace than a compressor. By the way, when you're checking all this stuff, don't have it wired into the system. You have to isolate the components. Okay, in this case, we have a start capacitor that's between 176 and 216 microfarads is my rating. Okay, so between my tested out, I'm getting 263. Okay, that is not a good test on this capacitor. Even within 10%, that's not a good test. Okay, so that capacitor has a problem. Now again, under this metal band here, there's probably a tolerance rating. They're normally between 5 and 15%. Okay, and you notice here, the brown wire is off that capacitor. Okay, so this capacitor is not in the circuit at this point. Important when you're doing the testing. Now, to troubleshoot the potential start relay, okay, again, as always, make sure power is off and discharge all capacitors, not just the start capacitor, because every capacitor is in this circuit. With your meter, test the resistance across pins 1 and 2. It should be a closed circuit and your resistance should be 0. If it's greater than 20 ohms, there's a problem with the contacts in that relay. Change it. Okay, because contacts within these boxes, within these sealed boxes, can start getting pitted, can start getting damaged over time. And any resistance in here will cause problems in your circuit. The voltage across a closed switch should be 0. Okay, voltage across a closed contact should be 0. With your meter, then check the resistance between pins 2 and 5. Your resistance should be between 3K and 16K ohms. That's 3,000 and 16,000 ohms. If it's 0 or open, OL, then the coil's bad. You have to replace the potential relay. Now, why? Then you're going to do one final check. Okay, take a resistance reading between pins 1 and 5. This tests the entire circuit through that relay. The resistance should be identical to the sum of your two prior resistances, the one across 1 and 2 and 2 and 5. If it's OL or 0, then you need to replace the potential relay. Once you've checked all the components, be careful and rewire into the system exactly how you found it. Okay? Now, real quick, these two voltage readings, okay, or those two resistance readings make more sense when we look at this picture here. The first one between 1 and 2 is across a normally closed contact. Okay, when you're holding in your hand, that contact is normally closed. It's a closed switch. Then you're going to take a second reading between pins 2 and 5. That's across that relay coil. Okay, between 3,000 and 16,000 ohms. Then you're going to check the whole circuit, and you're going to come across 1 and 5. Should be the sum, add the resistance here and the resistance here. Okay, so there you've checked all three terminals. Now, when this is powered, okay, if this contact is opening the way it should, once the motor starts, you should be able to get a voltage reading from 1 to 2. Because it's going to be voltage across an open switch. Okay, so you should get whatever your input voltage is between 1 and 2. If you do not, if you get 0 volts here, okay, then this relay is not opening. Be careful when you take these readings, okay, because it's normally in a very enclosed space. So that's how you troubleshoot these, okay. Once you've checked all the components, be very careful, rewire into the system. Okay, again, capacitors are pretty inexpensive, so if you have any problems with a capacitor, it is a lot cheaper to change the capacitor and the relay than it is to have to change out a compressor.